So we saw in our last module how Anderson's algorithm can be quadratic to cubic time in the size of the program. So I'm going to discuss another algorithm, which is a very popular algorithm called Steensgaard's algorithm, named after the person who proposed it. It's a near linear time algorithm, linear in the size of the program, and also linear space in the size of the program. And it's a May point to analysis, just like Anderson's algorithm, except that it has some extra heuristics or tricks to basically make it faster and smaller. And Steensgaard algorithm is actually used in compilers like LLVM because it is linear time. Compilers can afford linear time algorithms, but they cannot afford quadratic to cubic time algorithms. Okay, so recall that order n square space was required in Anderson's algorithm just for representing the May point to relationships. Because if there are n nodes in the points to graph, then the number of edges could be up to order n square, and so that would be the amount of space that is required to just store the information. In fact, we had also discussed how computing that graph can be, in the worst case, cubic in the size of the program. This algorithm is going to require constant space for each object or register or address. So Anderson's algorithm required up to order n space for each register, because each register could have up to order n outgoing edges, all the things that it could point to. And similarly, every object could have up to order n outgoing edges, and so on. So Anderson's algorithm required linear space for every object or register or address, but this algorithm will require constant space for every object or register or address. So let's see how that happens. The key idea is that whenever there are more than one outgoing edges, Q, let's say P is pointing to Q and R, then we merge or unify the abstract objects Q and R into a single abstract object, which we call Q comma R. So we unify the abstract objects. So, and the basic insight here is that if there's an object P that is pointing to two different abstract objects Q and R, then Q and R are probably going to behave similarly, and so we don't need to track their points to sets separately. We can actually merge them into a single compound object and then pretend as though they're a single abstract object. This is obviously at the cost of precision. But then, anything that R points to, just believe that Q may also point to that, and anything that Q may point to, R may also point to that. So when you merge or unify two objects, you are losing precision because you're basically saying that anything that R could point to, Q can point to, and vice versa. And this unification is transitive. So for example, if the original points to graph was P points to either Q or R, and then Q could point to either S or T, and similarly R could point to U, then because Q and R have been unified, then the new points to graph looks like this unified node could point to either S or T or U, coming from here. And then all these outgoing edges could be merged into a single abstract object, S comma T comma U. And because this is transitive, unification is transitive. And so this becomes S comma T comma U, and then whatever they could point to, that becomes V comma W. And you can see how this big graph here with many edges is actually reduced to a much smaller graph with only 3 edges. And so this is what unification in Steensgaard algorithm does, and this is really the key idea. This is the key change from Anderson's algorithm, which makes the points to information smaller, but potentially at a loss of precision. But the hope is that this loss of precision will be small for typical programming patterns, and that's what was shown empirically, and that's why this is a popular algorithm. So Steensgaard algorithm relies on the heuristic that all pointees would likely have similar points to sets. So if all pointees of a single object, so let's say of a single object P, would have similar behavior. So avoid tracking, separate tracking for them. Just unify them into a single node and just track them as a single abstract object, and anything that and you can just kind of unify all their outgoing edges as well, and do that transitively. There's a variant of Steensgaard algorithm which is the precision, which improves precision slightly, and which is typically used, which is that if U is not a pointer. So for example, in this example, let's say R is pointing to U, and Q is pointing to T, and if Q and R are unified, then the outgoing edges are U, T, and S. And in the original algorithm, we would unify all three of them. But there's a slight twist, or the slight precision improvement for this, which is that if among all the pointees or all the outgoing edges, if the ones only unify those outgoing edges or those pointees which are not pointers, or which are pointers, only unify those outgoing edges which are pointers. Do not unify those pointees that are not pointers. For example, in this case, U may be a scalar. For example, it may be an integer. In which case it can't have any outgoing edges. And in fact, when I unify, I don't unify U with S and T. So S and T get unified because they are pointers, because they could further point to other things. But U is not a pointer, so I leave U alone. And that's basically the precision improvement. And so the general rule is that if any outgoing edge or any pointee is not a pointer, which means it has no outgoing edges of its own, then do not unify it. And here's an example. Here U is not a pointer, and so U is not unified with the other outgoing edges or other pointees of Q, R, which were S and T. So S and T are unified, but U is not unified. And this helps because it avoids unnecessary outgoing edges from non-pointers. So, for example, in the previous graph, you may have seen that the points to graph said that U can also point to V, and U can also point to W, but U was not even a pointer, so we avoid that precision loss by using this simple precision improvement. And it seems to work in empirical, when evaluated empirically on real-world programs. Okay, so now let's analyze the space and time complexity of Anderson's algorithm. And I'm going to use the simple Steensgaard's algorithm. I'm going to use a simple Steensgaard's algorithm without the precision improvement that I just discussed in the previous slide. So, in the simple Steensgaard algorithm, there can be at most order n edges in the worst case, because after all, a node can have at most one outgoing edge, because if it had multiple outgoing edges, we would have unified all of them into a single edge, and we do that across all the edges, and we do that transitively. And so because a node can have at most one outgoing edge, there is only a constant amount of space that is required for every node in the graph. And so the number of edges in the points to graph is order n in the worst case. And that's a significant improvement in time complexity, because in space complexity over Anderson's algorithm, which had order n squared worst case space complexity. In Steensgaard, the space complexity order n worst case. It's a huge improvement. Imagine there's a piece of code which has millions of lines of code, then order n is just order million, but order n square is million square, which can be a very large number and may overflow our hardware resources. Also let's look at time complexity. So when I process a statement, so the time complexity is determined by how the transfer happens when you implement the transfer function of a points to algorithm. So for example, I could have something like x, let's say x colon equals star y. Then I look at, what is y pointing to? So let's say y is pointing to something. Let's say y is pointing to A. Then I look at what is A pointing to. So let's say A is pointing to B. Then I say, okay, now x can also point to B. So let's say x was already pointing to C. Then I say x can now also point to B. But the moment I do that, x can have two outgoing edges, and so I unify B and C into a single node. So the new points to graph becomes x can point to B comma C, and y can point to A, and A can point to B comma C. And so this is the new points to graph. So what was required in doing this transfer function? Well, I had to first identify the node corresponding to y, or in this case star y, which means y would have, because in Steensgaard algorithm the variant is every node can have at most one outgoing edge. Y will have only at most one outgoing edge. So let's say that one was going to some node, let's say A. Then A also could have at most one outgoing edge. So that is, let's say, going to B. So, and that's the node. That's what I mean by identifying the node associated with the RHS or the variables on the RHS. So in this case, that's B. And there will be only one such node in Steensgaard, unlike Anderson's where there would be up to n such nodes. And then you create an edge from X to that node and unify if required. Right? So X would also have maybe at most one outgoing edge already. Now you create one extra edge and then you unify these two. all these operations are actually constant time. So operation of creating an edge, because there's at most one edge to be created, and unifying if required, there is also constant time because there's at most one unification to be done. And so both of these are constant time operations. And so the total time taken, but the only thing here is when you identify the node associated with a variable, then so it depends on how you implement the unification and the identification. So depending on the data structure, the time complexity of identification and unification can be slightly different. And so let's say we use, one of the kind of easy data structures to use here is the union find data structure, which basically gives you order alpha n, where alpha n is the Ackermann's function, which grows very slowly, slower than log n, in identification of a node, and unification is just order 1. So if you recall, unification just involves addition of an edge, and you find or identification basically requires traversing edges by short circuiting as we are going, and traversing and finding the root and checking whether what the root of that cluster is. So that's the union find data structure that you may recall from your data structures class. Using that, you can do these operations in order 1 and order alpha n time. So if there are n statements and you can have at most n transfers, then the amount of time that it requires is order n alpha n. And so that's the time complexity of Steensgaard algorithm, which is significantly better than, it's almost linear time, slightly higher than linear time. Alpha n grows slower than log n, so this is slow. This is less than n log n. So this is a significant improvement over quadratic to cubic of Anderson's algorithm, and that's why it's typically used in compilers. So based on, Steensgaard algorithm was proposed somewhere in late 90s, in 1996, and when it was published, the result that was empirically shown was that Steensgaard algorithm was run on a 1 million line program, which was a Microsoft Word program, and this was an order of magnitude improvement in scalability over state of the art at that time. Steensgaard algorithm, which was used at that time, was field insensitive, but you can also make it field sensitive, in which case some of these tight space and time complexity bounds may need to be loosened up a little bit.